Hello everyone, welcome back to the Game Engine Development Workshop series. Before we start today, again, I have something pretty cool to show you, just a bit more about our scripting language. I now have it to the point where it is fully integrated with our engine. So I have this camera script here and I can just show you a bit about how this works. So I'll run everything and it's what you'd expect. I move around and the camera follows me. But this camera movement is actually, if I go to my main file here, all of the stuff that we're currently doing, just like getting, input directly and scaling it ourselves and all of that, like hard coded, that's not actually running anymore. The camera is entirely controlled by this script. And I won't explain entirely what it does, but basically this -1 is important here. So if I delete that, just make it 1, then my camera will move in the opposite direction as my player. So yeah, everything is like, all of the dynamic stuff is controlled with these scripts. And here I have the actual script that's controlling the player itself. You can see here this player.setvel is also commented out. That's no longer being directly controlled by C++. It's all through this script. So I get the state of the A and D keys, the W and S keys, and then I manipulate those, multiply them by the speed, and set that as my velocity. I also have this system that changes the state of my player. So you can see here, up to this point, we've just been using sort of stand-ins for the state. But I do actually have two different states here. They're named move and idle. They were set to the same sprite, but if I change that to D3 and I run this, oh no, they weren't. I was wrong. They were set correctly. But so this says if the velocity is 0, then set the state to idle. Otherwise, it should be setting the state to move. So now you can see when I move, it changes to, this bigger sprite, very cool, and then automatically changes back when it's done. I'm not sure why I have those things in the map as non-rigid, but I should be demonstrating that as well. You can see here that, like, the interaction there, as I begin moving, I change the state, and so I can't actually get as close to it. It's kind of weird, like you'd never have that situation, but it's just pretty neat. And then there's some other stuff here that basically just lets me spawn an item every 1 second, and it will spawn in the direction that I'm moving. So it's like I'm shooting a little arrow. And you can see here, there's not actually code yet for like controlling, for making them automatically despawn when they go out of bounds. So it's just spamming this error here. But yeah, hopefully that's something cool to look forward to. I'm pretty proud of that. But anyways, today what we're doing is more hitbox stuff. So I just thought I would touch on a few things that I sort of left out last time. First of all is the font size. I realized in the previous video the font size was pretty small, so sorry about that, but hopefully this is better. Another thing is I talked about, or I mentioned on the title slide here, that this only works for things moving at reasonable speeds, in quotes, and I didn't really quantify that. I don't think there is a way to quantify it. It depends on like the distribution of rigid objects in your world. But essentially the problem becomes when you have a lot of objects, you'll get a lot more subdivisions, right? Obviously the number of objects here don't warrant this number of subdivisions, but just ignore those for now. Look at the subdivisions. They get much smaller and smaller and smaller. And as they do that, the elements within them can get smaller and smaller and smaller. And more importantly, there is less area for elements that are in the same quadrant to be contained within. And what that means is that elements that aren't that far apart will potentially be in completely different quadrants. And so if you have a small thing moving very quickly that's in some quadrant, like a very divided small quadrant like this, and it's moving very quickly at some other object that is in a different quadrant, then it'll just pass right through that. Because for that frame, that fast moving object has the potential that its velocity just completely like skips through the object that it's pointing at, and it won't actually be checked against that object because it's small enough and fast enough that it's contained in only a very small space like that. So this isn't a problem for like practical scenarios, but I don't know. It's not something I'm completely happy with. I want everything to be as general as possible, but that might simply be impossible when you get into problems that's difficult. So anyways, that's why I said reasonable speed, but again, that's not going to be a problem for this. The other thing I wanted to show is in this dumb example here that's just generating a 10,000 hitboxes running in debug mode, of course. There's a problem with this I didn't show, which is I'm holding W and D right now. So I should be moving up and to the right. But you can see I sort of get stuck at the corners of these things. And going the other way, that's sometimes true as well. And the reason for this is the order in which our collisions are resolved. So I'll do a simple paint thing here. So if I have like a bunch of different hitboxes that are right next to each other, as I do in this case, I'll just draw 3. And then I have my player moving along. When I get to a corner, something weird can happen, which is that, well, let me actually draw this in to match what I was just doing there, where I was coming at it from the bottom and I was moving up and to the right. So that's our scenarios. I'm coming at it from the bottom here, and I'm moving up and to the right. So what happens is this rectangle on the right here gets sort of arbitrarily resolved first, and then this one gets resolved second. And the result of this is that this collision will push this player rectangle back, as it should. So if my player rectangle is moving at it like this, then this first box right here will say, okay, you shouldn't be there. I'll move you back out there, which is fine. But then now the second one gets resolved and pushes me out here. And again, this it's okay in that it correctly resolves these collisions. It's not really a flaw in the algorithm per se, but when in the way that this is being applied in our game engine, where we want smooth, like dragging, sliding movement like this along any arbitrary surface, it is bad. It's not a desired result. And the reason it's not desired is because these should be getting resolved in the opposite order. This should be 1, and this should be 2. Because then what happens is as my player's moving along that same trajectory, like this, say I get to this same point, now this one isn't being resolved for this one is. So it says, okay, I'll push you back out to where you should be, and then there's nothing left for this second one to resolve. So it doesn't push me back this way. And that's the desired result, is only the direction of movement that is causing an intersection gets resolved. And so in this case, I would just correctly slide along the bottom there. And so that's what leads to that sort of sticking effect, where the ones to the right of me are being resolved first, and so they push me left, and then I get pushed down, where I should be getting pushed down and then not needing to be pushed left. So that's another thing that we'll have to consider. Okay, so I did sort of leave off here at some point in our PowerPoint. I believe it was node.elements. Yeah. So, well, I don't actually want to present this. I'm not sure how I want to do this. What I was planning to do is have these slides up as like a reference as we're developing this stuff, just so we can like come back to it. So I think I'll just drag those off to the side there, and then we'll actually start writing. Okay. So we're gonna write all of this stuff. I'm gonna write it in our math library. And it's all going to be in a single file called Quadtree. The reason it's in a single file is that we have two classes that are completely like intertwined. They're dependent on one another, and so they both need to be able to reference one another. And the way we can do that, and that we have done that so far, is very simple. It's just we declare everything in a header file and actually define it later in a separate C++ file. And that's like the right way to do stuff. But this is like a library, so we really want everything to be kind of headers. And also just adding C++ files makes configuration a bit of a pain, where like those C++ files will automatically get marked by Visual Studio as like use a precompiled header. It's just sort of a mess. So we're going to be defining everything and declaring everything and defining everything in a single file here. So I'll just include everything we need up front. Going to need both unordered map, unordered set, and regular map, and regular set. Then we'll need core, range, vec2, basically everything else in our math library here. So this linked list node, we'll see in a minute what that's used for. And I guess actually we could go ahead and write that. It's like 4 lines. Nothing interesting to say here, just classic doubly linked list node implementation. Okay. So I'll sort of mark off this section as Quadtree node.h. So this is, if you remember, we have sort of 2 components to this. We have the node and we have the elements. And they're very interdependent, so we have to define them all in one file. So I will forward declare the element class here. But we will be writing the node class first. Okay, so I'm going to do some type defs here just to make typing all this easier. We have node, element, and then linked list node, element node. And then for convenience, I'll mark Quadtree Element, just copy that, as a friend class. Okay, so let's consider what we actually need here in our node. I'll go ahead and define a couple constants. The number of children, just so we don't have 4 all over the place. The minimum dimensions, which we'll talk about when we get there. Obviously, I need other nodes, my potential child nodes that I might have, which is an array of 4 node pointers. And I'll also store a pointer to my parent. Then I need a vec2 float position, a dimension and count, which will be the number of elements I have. But how do we actually store these elements? Well, let's examine that. So we could use an array. We could just create an array of the length of the threshold value that we give, and say I'll put all my things in there, and I'll keep track of like where they are. But there's a lot of annoying overhead to that. That it's not like hard to implement. It's just annoying. I don't know how else to say it. It's like there's just no reason to do it this way. So when adding stuff to the array, we have to know which index to add to next, because you can remove stuff from anywhere in the array, and so you might have like open slots that you then have to keep track of. And when removing, you might have to shift the array if you don't want to keep track of those open slots, or you'll have to keep track of the open slots. When iterating over a node's contained elements, we also have to check for that each one actually exists, because we may have removed it. Alternatively, if we don't do that, we can guarantee that they are stored contiguously in the array, but then you have to do some extra processing when you remove. You just have to shift everything potentially, which is not like a huge deal because our threshold value is going to be very low compared to the order of magnitude of like the number of things total that we're storing, but it's just annoying. So these are our requirements. We want it to be clean and simple. We don't want any extra iteration. We don't want to iterate over more things than we have to. So we want to know basically how many things we actually store, or are currently storing, rather than just how many things we have the space to store. And we want order one add remove. So what we need is a linked list. Add is order one, because we can just keep track of the head of our linked list and make the new element. Whenever we add a new element, we can make that the head. So it's essentially a stack, but it doesn't matter at all. The order doesn't matter. And then remove is order one, provided at least that we have a pointer to the linked list node containing the element we want to remove. That's sort of like classically the trade-off between linked lists and arrays, right? Is that arrays, they're more expensive to operate on unless you're like adding to the end. Adding to the front, you have to shift everything to the right. Removing, you have to shift everything right of the element that you're removing left to close the gap. But linked lists, adding to the front and perhaps the end are order one. You just sort of rearrange the references. But getting to anything in the middle is said to be order in time, because it's not random access. You only have a pointer to the head and maybe the tail. But we can sort of just get around that entirely by just having every element within our node store the pointer of the linked list node that it contains, or that contains it. And that probably sounds confusing, but you'll see what I mean. Basically, this is just free order one, free efficiency. And this is clean and simple, because all we have to keep track of is the first linked, the head of our linked list, and the number of total nodes that we have in our list. So we don't have to do any extra processing for add and remove, and we can guarantee clean iteration because we don't have any empty spots. So that's what we're going to be doing. That's how we're going to be storing the actual elements within our node, within a linked list of elements. Okay, so I'm just going to write out like all the method signatures for each class first. So we'll take in the min and max like points that this Quadtree node has to span, which we'll see much later, maybe not even until the next time. We won't be using that constructor internally. Just go ahead and delete these things. And we have quite a few pointers here, so we need to clean them all up. In the Destructor, we'll have add. And then I have a bunch of simple methods here. So we can check whether or not a node is divided based on just whether or not its first child pointer is null pointer. Because if we can guarantee that whenever a node is not divided, its children are all set to null pointer, then this is just a very fast way to check that, and we don't have to keep like an extra boolean around. And we'll have get first element. Just returns the head of our data list there. Get count. And most of these methods are just for like compatibility with the outside world, essentially. I sort of touched on this last time, and we'll see as we get into implementing this that it's designed to be as general purpose as possible, like as abstracted away from the rest of our engine as it can be, which it is, like, and that's how it should be. And so basically, when we start writing the element class, there are several virtual methods that we'll need to override and implement for our specific use case. And if we want to access information about a Quadtree node within those derived classes of the Quadtree element, we'll have to do that through public methods, because like friend status doesn't extend to the children of a type. So even though we've marked this sort of base abstract Quadtree element class as a friend of the Quadtree node, the classes that we'll write that actually extend this and implement the necessary functionality won't have access to all of the underlying data here. So they'll need to use this sort of public interface. But other than those, most of the functionality here will be private, including this constructor that we'll use internally. So we'll have delete element, which, as I was saying, takes an element node directly. Have delete data, which will clear all of its children, or all of its elements. Have divide. Unordered, oh my god, I can't type. Unordered set, there we go. Divide just sort of takes all of the elements contained within this node and pushes them down to children, and merge does the opposite. It takes all the elements in children and brings them up into this node, then deletes the children. Okay, so that's our Quadtree node. Next we have the Quadtree element. So I'll do the same thing as up here. Grab all these convenient type defs. And I'm putting these protected instead of private because, again, we will be inheriting from this class, so it'll be nice if the children also have access to that. And then one last thing, in protected we'll have the struct collision info, which will basically just store like the variables we're storing here, normal, contact, and time, just all in one, as well as the element that was actually collided with. So we have position, dimension, and velocity. We'll have a virtual destructor. And we'll have a big important function here, resolve collisions. That's going to be virtual. And I'll sort of explain why some of this stuff is virtual once I've written it all out. We have move, which takes in like the new values of the object that this element represents. Remember, like, we're not going to be adding dynamics directly into our quadtree. We're going to be, each dynamic will have a quadtree element that sort of represents it in the quadtree. And so when our dynamic moves around and changes state and stuff, we need to send this element those new values because they're not linked intrinsically. So that's move. Then update performs collision checks and resolves them. Then I'll just have getters for our three vectors there, cause, vel, and dimension. Okay. So we have a constant here that I'll talk about like when we get there. It's super not important. And it looks weird and arbitrary because it is. Again, I'll talk about that. So we have our position, our dimension, our velocity. And then now we get into the tricky stuff. In order to ensure like the fastest operation times for everything, we need to cache like a whole bunch of stuff. Because whenever we want to change something about how this node interacts with the tree that contains it, or sorry, how this element interacts with the node that contains it, we don't want to have to go searching for this element. We need to know where it is and just be able to go straight there. We have to cache here. We have a set of nodes, or sorry, a map of nodes, which are quadtree nodes, so the things that actually contain our elements, to element nodes. And element nodes are those linked list nodes that actually store the elements. And that's what I was saying, like this is the reason that removing from a linked list in this case is order 1, because we don't have to search through the linked list. We just have we store our own position in it. The next thing is a set of nodes called mGrandparents. So that's going to be for every parent in our mParents map here, we'll have that parent's parent node in our grandparent set. Okay, then we have some more virtual methods. Is contained by, which will be used when adding to a node. And then the actual method to check whether we intersect with another element. These pointers should all be const, really. And it might be cleaner to pass in just a collision info there. I might look into that. So we have a method add to here, which will just be it'll be used actually by the node class when adding an element into a node. We just have this add to because like a bunch of stuff has to happen with these maps and sets, and so it's cleaner to do it in here. Same thing for remove from. We have delete, which will remove it entirely from the tree. And then just some helper methods here. So some of these won't really make any sense until we actually start writing the stuff for this element class. But unfortunately, because all of this stuff is in one file and because it's just so intricately connected to everything else, I sort of just opted for the simplest approach of just going through everything in order, just writing it in the order that it's written instead of jumping around everywhere. So a natural consequence of that is some stuff will not make sense till later. Okay, so that's that. Now we can actually start. That's everything we need declared. Now we can start defining it. So we'll do node first, and then element later. Okay, so we'll start with the constructor. Which takes in a min and max vec2. I don't really have a good way of like explaining what these are, but they basically just define like the region of abstract 2D space that this Quadtree node should control. Because we don't want our quadtrees to just have some like arbitrary large size. They should be as small as possible while still being able to take care of our whole world. So when we actually finish writing all of this stuff and then integrate it into the engine, this constructor will be called, and the min and max will be set based on values in our chunks. Okay, so in here, I'll have a vec2 called diff, which will be max minus min. So just sort of assuming that min is less than max. And this will give the, as I'm saying, like the entire span of what this, the amount of space, the area that this Quadtree node needs to be able to control. But as I sort of touched on last time, the size of our Quadtree nodes cannot be arbitrary. There are, let me see if I can find the slide, but there are a couple very important restrictions on size for everything to work correctly. So we saw it here in this node.divide method, where we have this min size, and in the code here, I have that as 2, I think. Where is that? 2, min dim. So this is, it's just the minimum like side length of a Quadtree node, because remember every node is a rectangle. And the reason it's 2 is that, going back to paint here, let's say I have, for simplicity, I have some square. This is my Quadtree. And it's really small. It's like 4 pixels on each axis. And then this upper node here is further divided. So what this means, well, I guess I can write it out explicitly. Each of these will now be, sorry, I gave impossible numbers. That should not be 4, that should be 8. So each of these smaller quadrants within this top one here are 2 pixels by 2 pixels. And I mean, what that means is that, you know, there are only 4 pixels that can be contained within that. And so this is sort of a like value that is based on the way our graphic system works. where we are loading, like everything in our world is drawn using a sprite. And obviously you can't have a sprite that's smaller than 1 pixel by 1 pixel. And so when we are dividing our quadtree nodes, we need a cutoff point so that we don't just keep dividing, to infinity, because we could do that if we could have our dimension be a float and go from 2 to 1, 1 to a half, 0.25, you get it, 0.125, just to infinity, or to 0, but infinite divisions. But that doesn't make any sense. There's no need to do that, and it should never happen that we have to do that, because all of our stuff, like every object in our world, takes up at least the amount of area that is 1 pixel by 1 pixel, because that's the smallest possible dimensions of a sprite, of an image. And so if we ever get to the point where we have a 2 pixel by 2 pixel quadrant, these minimum dimensions that we've set, and this is not like an actual subdivision. I'm going to fill these in with different colors to show that there are like 4 different objects in here. So each of these pixels is a different object, and each of those objects is only 1 pixel in size. If we ever get to the point where we have some other 1 pixel by 1 pixel thing that we're trying to add, that is an error. That's invalid, because you can see here it means that it's already intersecting with stuff in our tree. And again, I mentioned this last time, but we don't have a way to resolve that. Our implementation depends on things initially not being intersecting. And as they begin to move around, it handles any new intersections that crop up. But as stuff is added, it has to already be not intersecting. And so this case, based on just that physical fact about our game world, where everything is at least 1 pixel in size, means that the minimum dimensions for a quadtree node for any quadrant should be 2 by 2, because any further than that means that we have intersections, which we can't resolve. So that's an error. So that's one of the constraints on size, and that's why we have that minimum dimension value of 2. The other constraint on size, that's like the small constraint. The big constraint is that in order to get to this point, for a quadtree that has to span an arbitrarily large space, in order for it to properly be able to divide to the point where it has 2 by 2 quadrants, exactly 2 by 2, the side lengths of the whole quadtree, like the root node, must be a power of 2. And we can see this quite clearly. We start with 16. We divide by, so if just forget about all these numbers here. If this length here is 16 pixels, then each of these would be 8, and then those further divide into 4, and then 2, and then that's as far as we go. But if this was some weird number like 30, that'll divide into 15, which will divide into 7. This is all integer division, which will divide into 3, which, we can't get to 2 from here, because when you divide 3 by 2, you get 1. So our like the dimensions of our root node have to be a power of 2. So we'll just come into our math file here, and define a dead simple function to handle this for us. Which will take in the base. So in our case, 2 will be the base, and then b is the minimum value that we're trying to achieve. So if in that example, if our base is always going to be 2, but then our value will be 30. So this function will look at that value and say, okay, so I need some power of this base that is greater than this, and so it would sort of round that up more or less to 32, the next power of 2 above it. So we're just going to do this with a loop, with a dumb loop. So we'll start at 1, and while the current value is less than the intended value, we'll just multiply by base, and then return cur. Start from 1 and go until we're bigger than the value. So our initial dimension here will be the next power of 2 bigger than the area that we actually need to span. Okay, but again, we won't be using this constructor until probably next time. Next we have our Destructor. So in this, we need to clean everything up. So we need to delete our data, all the elements we contain. And then for each of our children, we need to delete them. And this will call their destructors, and they will delete all their data, so on and so forth. Okay, now we're going to get into some meat here. We have the add method. Okay, so our add method is going to be recursive, because when we create an element, we obviously don't know which node it should be in, so it's not like we can just go to all the nodes that it needs to be contained by and add it directly. We need to find which nodes it needs to be contained by. So we'll start from the root and then sort of recurse our way down until we found everything, every node that contains our element. And in that process, we will inevitably hit some nodes that don't contain our element. And if that's the case, we just need to return. And we'll use the isContainedBy method, that virtual method of our element class, to determine whether or not this node, this element, belongs in this node. And the reason this is a virtual method is because that way it's up to the programmer to define the geometry for this. The Quadtree is sort of a universal structure that can operate on 2D space, regardless of what's contained within that 2D space. It doesn't really care. And so the elements are actually what define all the actual interactions that take place. The node just handles stuff efficiently, moves memory around so that there aren't a whole bunch of pointless collision checks that happen, but the elements are the ones that actually perform those collision checks and need to know how to resolve them. And so again, in our case, this contained by method is just going to be super simple, just axis align bounding box, just because it's a non-rotated rectangle. But my point is that if you wanted something more complex, you could very easily do that. Like, it wouldn't be terribly hard to extend this to work with circles or, insided polygons if you want to use a much more advanced collision detection algorithm. So that's why isContainedBy and resolve collision and intersects, all those methods on the element class, are virtual. So if we're not contained by this element, if our element is not contained by this node, and our node doesn't have a parent, meaning it's the root of the tree, that means that this element doesn't belong anywhere in the tree. So because remember, our root is like the biggest node. It's the whole world. All of its children and children will be way smaller than it. So if our root doesn't contain the element, nowhere else in our tree is going to be able to fit it. And so that's an error. Like, we've inserted something that we do not have the space. Essentially, this is an element that is somewhere in space that is not controlled by this tree. And so we should print some according error. And that's actually the error you were seeing earlier when I gave that example of that simple script that when I just pressed the spacebar, it spawned that thing that flew off in some direction. Those eventually flew outside of the Quadtree, and that's why it was spamming that error. It was saying Quadtree cannot contain this element, whatever. So we'll just print a nice debug message here. nicely formatted so it's very clear what's going on. This is just going to be a lot of typing. And at this point, we'll return. This element is not contained by this node. We have nothing else to do. We'll just leave. The next check we'll do is if our im count, so the number of elements we already have, is equal to our threshold value, we will preemptively divide this node. Because remember, any Quadtree node can only contain up to the threshold value of elements, and then once it gets past that threshold value, it has to subdivide and push some of those or all of those elements down to its children. So if we're already at the threshold before we've added this next one, we'll go ahead and divide. And then if we are divided, remember also that nodes store one of a list of elements or 4 children. It can't have both. So if we are divided, we're not going to add this element to ourselves. We're going to just push it down to our children. So we'll go to each of our children and call this method on them. There's the recursion element there. And then we have sort of another base case, which is this current node is not divided, and so we need to add this actual element node to it. So this is where like where it actually happens, like where the element actually becomes contained by this tree. So we'll create a new element node. That node's data will be our element. The previous pointer to the previous will be null pointer, again just because we're treating our list of elements in each node sort of like a stack, not for any reason, just because it's convenient, where we will be adding and removing, well, not removing, but we'll be adding to the head every time. And so the previous element is going to be nothing, because thinking from left to right, the head is the leftmost element, so there's nothing to the left of it. Now, if we already have some elements, so we already have a head to our linked list, which is imData. If imData is not null pointer, then our node should point to that, because that will be on the right. So node.next will be imData. And then because this is doubly linked, our current head value on the left of that should now be our new node. Then we just set imData equal to node, so node is the new head of our queue, and we increment our count because we are now storing one more element. Now we do the sort of add to, which takes in a node pointer and a linked list node pointer. So the node pointer will be this, and the linked list pointer will be node. And this just, when we write this, this will handle like adding everything to the parents and grandparents list, all that stuff. Just because it's cleaner to do it as part of the actual element class. So I'll just draw a diagram for that linked list thing, just in case I wasn't clear. So let's say we have 3 elements and we're adding a 4th, and I'll make that a different color. Okay, so the links between, oh, I messed it up. The links between our nodes, the existing nodes, will look like this. It's all doubly linked. And this will be imData. This is our head. So again, thinking from left to right. Now we create this new node, this red one, called node. And whatever this points to on the left, obviously nothing. There's nothing to point to on the left, so we set that to null pointer. But then if imData does exist, so we already are storing some elements, then the pointer to the right of our new node will be that head, which you can see here. Obviously that's true. And that head's left pointer will be our new node, which again, obviously is true. And then all we have to do is, well, we increment the count, obviously, because now we're storing one more element, but we just move our head pointer from this previous one to the new one. And then that takes care of everything, and this cycle can continue for as many nodes as you add. Okay, so now we'll have the constructor that we'll actually be using. The private constructor. Which takes in a position, a size, which is the dimension, and a parent. And we don't need to do anything else. No calculations need to be done. Okay, now we'll handle our deletion stuff. So delete element, which will happen on an element node element. So at this point, I'll go back to the diagram here. So when we added this red node, this got added to some element in its imparents map. This new node got put somewhere in there. And now we are deleting this element, or not deleting it, but we are removing this element from this specific node. So we already have this node pointer. So all we have to do is go to it. That's what I was saying. So that's where this element node pointer is going to come from. It's going to come from an element that stores it. But for the sake of example, it'll be much better if I show this as like this node, somewhere in the middle. So if we want to remove this node, a couple things have to happen. If we just delete it, that won't quite work. Because let's see what happens if we just delete it. We have, just get rid of that box. And then these arrows, that box is now gone, so it doesn't point to anything. But these two boxes still think it's there. They're still pointing to that memory address. They have no idea that it's gone. And clearly, that's not going to work. So what we have to do is sort of fix these linkages and then delete the node. So we need to make it so that this node, call this A and this B, so that A no longer points to in. It instead points to B, and B also no longer points to in. It points back to A. So sort of just taking this out and squishing these two up against each other. And then at that point, we will actually delete in itself. So if we have some node to the left of us, then we will get that node to the left of us and set the node to the right of it equal to the node to the right of us. And then we'll just do the exact same thing for the right side, where if we have a node to the right of us, we will get that node to the right and set its node to the left equal to the node to the left of us. And then we do have to do one last fix here, which is that if we are deleting the head, if this element node just happens to be the head of our list, then we need to move our head pointer to element.next. Move our head pointer one to the left. Then we will delete our element and decrement our count. Okay, next we have delete data. Which will just delete all of our elements. So starting at the head and going as far as we can, we will get the next one in the queue, or in the list, delete the current one, then set the current one equal to the next one. This is quite important, setting mData equal to null pointer and mCount equal to 0. So now that we've actually deleted all this stuff, just sort of cleaning up after ourselves, making sure this doesn't have a stale pointer to somewhere that's been deleted. Okay, we have another pretty big method here, divide. So this method has to be recursive. And the reason it has to be recursive is because we can't guarantee that when a quadrant is divided, it will be what I just term I made up, a clean division. So let's look at an example of a quadtree. And we'll put 4 elements in it. They do have to be rectangles. So this is sort of an artifact of the fact that we are using rectangles instead of instead of just points. This is bad. I shouldn't have drawn those lines yet. Okay, so let's say we have these 4, and we're adding another one. So they're all like quite tightly packed. So we say, okay, so we're above the threshold value now, so we'll divide. But, oh no, I still have above the threshold value in one of my quadrants. I can't guarantee that this will always result, like one division will solve the problem of having more than the threshold value in a given quadrant. So I have to divide this again, and in this case, just one more division fixes that problem nicely. But it could be very many, depending on how small your things get and how close together they are. But the first thing we need to check is if we can actually divide. This is where our minimum dimension comes in, where if we're trying to divide into a quadrant that's smaller than 2 pixels by 2 pixels, objects in the tree, objects have been inserted into the tree that are already intersecting. They must be. That's just a fact based on like the physical reality of our game space, our game world. So we'll just print an error. Again, we have no sort of recourse here. We have no way of actually fixing this. Which you could. It's not that it's impossible. It's just that we don't have that, and it wouldn't be very interesting to program. So we'll just ignore that problem. Okay, so when dividing, first we have to go through all of the elements that this node contains and sort of remove their references to this node. Because remember, each element has a map of parents and grandparents, and it like knows where its location is in the tree. But now that location is changing, and so we have to remove all the stuff in this node that points to this node, or all the stuff in each element that points to this node. So we'll do that with the remove from this. We'll do that for each element. Once we've done that, I'll just have a vector here for convenience, so I can loop over everything. We will create our children. Because remember, at this point, they don't actually exist, because we're storing nodes, and we can't store both nodes and children. So we need to create our children. And so our nodes, we'll be using the internal private constructor. Our node's position, position being the bottom left corner of the quadrant, will be the position of this node plus one of these offsets. So these offsets are like in no particular order. It doesn't really matter the order that you do this in. But what they do is they're multiplied by our dimension. So we start at the bottom left of our current quadrant, and we just set a new quadrant, a child quadrant, at that position, which we need. But then we also need one in the bottom right, and then one in the top right, and then one in the top left. So we get these offset sort of multiples, and then multiply those by our dimension. The reason it's 0.5 instead of 1 is because we don't. Our new each of these quadrants will be half the, well, it'll be a quarter the size, quarter the area, but half the length of our parent quadrant. So that's why it's 0.5. And then dimension will be our dimension divided by 2, and then the parent will be this. Okay, now for each child, we will sort of start our list over here and add each of our elements to this child. And the nice thing about this is that it's very clean, because our add method handles all the logic of, do I actually need to add this? So we don't have to do any checks here. We just say add it, and it'll figure out if it needs to. And then we add the current child to our children array. And then finally, when we're done with everything, we can actually delete this node's data, which is these elements, because these elements now exist wherever they need to in the children, so we need to delete our local copy of them. Okay, next we'll write merge, but before that we'll do a sort of helper method. This may seem a little weird, and it is a little weird. So we're going to call this on a node to get like the number of unique elements that are contained within all of this node's children. And so calling this, and it's going to be recursive. So calling this on a node that's not divided, we actually do have elements contained within it. So we need to get those. We will insert each one into our set. It's a set because we want unique elements. We want no duplicates. And because these are all pointers, they're element pointers. This is very simple. There's no we don't have to overload any equality operator or anything. It just looks at the integer value that pointer is and compares it. Otherwise, if we are divided, then we will just recursively call this on each of our children, passing along the same set. Okay, now we'll do merge, which is the method that's actually going to use this. We do another check first. If we're trying to merge a node that's not divided, that doesn't make any sense. So we'll just return. And then the first thing we need to do here is see how many unique elements are contained by all of our children. Okay, so a couple things here about the way I chose to write this. So this takes in a pointer to a set. It takes in a pointer instead of a reference, because I think when you are writing to a value, you should never pass it in as a reference, because that makes it unclear to the user of the function that that value can be modified, or at least less clear than it is if you give a pointer. Because if you give a pointer, it's sort of expected that you're going to be changing the value, because that's how it was done in C. That's just sort of the, like syntactical convention that's existed for 50 years. But the bigger question is why don't I just have this method return an unordered set. And the reason is because it's recursive, that would get kind of messy, and there would be a lot of copying of data and everything. And this thing, we want to make it as efficient as possible. So I've sort of taken some liberties and doing some weird like memory allocation choices that I'm not sure if they have any effect. It's most of them are sort of like theoretically this will be faster in my head, and so that's why I've done it this way. But the biggest question is like, should this even be recursive? This get unique elements, because merge, we're going to be calling it on a node that is guaranteed to be a grandparent. It's guaranteed to have just just like one level of children. And the reason that's a guarantee is that, well, maybe it's not actually. I don't know. I don't want to like explain something and explain it incorrectly. So all I'll say about like why this is recursive and why our merge method won't be recursive, but why divide is that there's like some mix of styles here. Well, not styles, but some mix of recursive and non-recursive functions based on like certain guarantees about how these functions will be called for this implementation of a quadtree. It's very messy, and I don't even remember it fully correctly, obviously. So I'll just sort of leave it at that. That like acknowledging that it's weird that some of them are recursive and some of them aren't. But essentially, merge never needs to be recursive, but this might need to be recursive. And so I just go ahead and take the safe option of creating this memory once instead of having to, for each of these, like append a set to another set and do a bunch of moving around. Okay, so once we've got all of the unique elements that this node's children contain, we might need to merge. So if our elements.size, so if the number of unique elements is less than or equal to our threshold value, then we can merge, because what that means is that we can just take all of those elements that are in our children, bring them up to ourselves, and we'll still have less than or equal to the threshold value, and then we can just delete our children. We don't need them anymore. Again, the sort of like theory behind balancing all of this stuff, our constraints, is that we want to have as few subdivisions as possible while still adhering to the threshold value. And that's what we see here, is this merge function like isn't technically necessary. You could just leave stuff divided to infinity, and as stuff moves out of it, you just leave it divided. But that can lead to slowdowns. That's as stuff gets more divided, there's more overhead for moving stuff around, and so it's best to merge previously divided cells back into themselves, I guess. So this is essentially just going to be the opposite of divide, where we'll go through all of the elements in our children, and we'll do remove from this. Actually, I don't think that's right. I can't remember. I think it's we'll erase this node from each of these elements' grandparents, because again, merge is only going to be called on a grandparent node of an element. The definition I'm using there is that the parent of an element is the node that contains it, and then the grandparent of an element is the parent of that parent node. And obviously, if an element is contained by a node, that node is its parent, that node can't have any children, because each node contains either elements or other children nodes. And so that's why we erase from grandparents here. We will be merging on grandparents, not parents, because the parents won't have any child nodes. And go through each of our children and remove them from our parents list. Then we will actually delete our children. And then set each one to null pointer. Always best to do that. It's very hard to debug if you mess it up. If you have some stale pointer, you will not know where it comes from. And then finally we add. So this is just, it's like exactly the inverse of our divide method up here, where we remove all of our elements from this node, add child nodes, and then delete our own data. Here, we delete our child nodes data, add children, and then add our previous child nodes data to ourselves. And all this should be in that same if statement. I don't know why it's not. Like that. Okay. So that's all of the stuff for our Quadtree node, which is good. Now we have our Quadtree element. Probably get part of the way into this, and then I'll have to call it for today. So Quadtree element. This constructor just takes in some vec2s, position, dimension, and velocity. Like that. Nothing else needs to be done. Okay, we have another big method, two big methods in a row here. We have move and then update. So move, again, the purpose of that is that it's the step where the object in our engine that this element represents is updated to reflect that engine object's like latest values. Values meaning position, velocity, dimensions. And I should keep these in the same order just to be consistent. Position, dimension, velocity. Okay, so this just takes in the new values of those and then the sort of root of the tree that we need to add to, because if any of these values have changed, we need to remove ourselves from our current position in the tree and add ourselves back into the tree. And we know that we need to do that if the new position doesn't equal our stored position or the new dimension doesn't equal our stored dimension. Because in those cases, well, if we've moved, obviously we might be in different quadrants, but also if we've changed our dimensions, then we might have shrunk, so we're no longer in certain quadrants, and those quadrants may need to be merged, or we've grown, and we need to add ourselves to more quadrants than we're currently in. So we'll just copy host values. And now we have some interesting logic here. So we'll copy our set of grandparents. So I was talking about where was it? Up here, like sort of making choices about when memory is allocated, making sure it's as infrequent as possible. For a set or a map, that is actually impossible. Because sets and maps under the hood are just implemented as red-black trees, and those they're truly trees. They're like essentially what we have here, where each node like stores pointers to its children, and so whenever you add a value, it's that like it will have a node allocated for it on the heap. You can't like reserve size in a tree the same way you can with an unordered map or an unordered set, which is just a hash table, so it's just an array. And that obviously you can reserve as much size as you want. So this set we do actually, like we don't have to create it every time move is called, but there's no benefit to not doing that. So we'll remove from our parents. we will clear our grandparents list. Then we will add ourselves back into the tree. So this will just remove like it'll clear our list of parents, and this obviously clears our list of grandparents. So essentially at this point our element thinks it's not in the tree, and then we add it back into the tree. Or it's actually truly not in the tree. Remove from parents, in addition to just clearing that map, will actually it'll actually go into the tree to each parent node and remove itself. So then we add ourselves back, and then at this point we have a new list of grandparents. That's part of the adding process, is when we add something, our grandparents list gets updated. And these grandparents might not be the same as our original grandparents. And in that case, like, well, this isn't a very good logic, but like, in our new grandparents, if they're not part of our, if they are part of our original grandparents list, we want to remove them from that list, because what that gives us is, after the end of this loop, our original grandparents list only stores the nodes that were our grandparents in the old position, but now that we've moved ourselves and removed all of our new grandparents, it only stores the ones that were there previously. And that means that we are no longer part of them, and so those nodes may need to be merged. And so we just go ahead and try to merge all of those original grandparents. So that's what happens if we have moved or grown or shrunk, like we need to move ourselves in the tree. If we haven't, then we don't need to do anything here. We can just copy those new values and move on. Okay. So there is, it turns out, a pretty sneaky bug in this implementation of move. We're using a set, and I kind of explained. A set is an ordered tree structure. It's a red-black tree. The default functor that is used for ordering this set, for determining order, for determining how nodes are positioned in the tree, the default functor for that is standard less, which in this case, like, works. It is valid. I shouldn't say works, because it is, there is a bug. But it is valid because our set is storing pointers. And if we actually go, let me bring up the thing here. If we actually go to, so we can see here, template class set, class key, compare is standard less. So standard less is, if we scroll down, there should be a list of all the stuff that it is. No, there's not. Well, I don't know. Somewhere on one of these pages, there's a list of like all of the types that this template struct is like. It has specializations for by default, and one of those is just a generic pointer type. There's actually, like, I guess a further, like, partial specialization of it, I guess, that has a class T star, and for any pointer type, this method is defined essentially. Which makes sense, because pointers are just numbers, and so standard less, you can just compare two numbers. It's natural. But it's not what we want. Because why this isn't what we want is because standard less will produce a random ordering, because we have no control over the way that our nodes are allocated in memory. We have no control over what the value of these pointers are. And the values, like the arbitrary random values of those pointers, determine the order of our tree structure here. So let's sort of like consider why this could even be an issue in the first place. So I'll present this. So we have a very simple Quadtree. We have these 4 red rectangles, which we're not interested in. We are interested in this blue one. So this blue one is going to move. And its parent nodes are outlined in green. So you can see that, well, apart from this one over here, but that's not important. So its 2 parent nodes are outlined in green, this one and this bottom one. And then its grandparent nodes are in orange. So the parent of this parent node is this one. And then the parent node of this parent node is this bigger one. Okay, so the blue object then moves here. So the resulting tree should be this. This should all get, merged back together. But also the parents and grandparents switch. Because now it's only part of this, so its only parent is this, and its grandparent is the root. But our node.merge function is not recursive. And maybe it should be. I don't know. Again, like I'm sort of admitting here, this is not perfect. It's certainly I would call it a clunky implementation. But so our merge method is not recursive, and so we need to make sure that we merge nodes in the correct order. The reason for this is that when a node is merged, all of its children are deleted. So in a case like this, if we merge this outer grandparent, this bigger orange square, before we merge this inner orange square, we have a memory issue because this outer orange square gets merged fine, everything works successfully, but it deletes all of these children. And then we call from our element class, we call merge on this node, which at this point has been deleted. And so obviously calling a method on a deleted object is an error. So let's look at that to see what I actually mean here. So we just have a set of node pointers. And when we merge each one of them, that's all this merge method is going to be. It's just going to be a loop where we go through all of these and try to merge them, essentially. When we merge each one, we don't like update the state of any of the rest of our nodes to say, hey, I've been deleted, or something like that. And so what we need to do is to prevent this from being an error and from getting like stale pointers, is we need to merge from the from the inside out. In every case, we need to merge smallest first and then biggest. Because that way, no children will be deleted that are then subsequently attempting to be merged. And in order to control the order in which our nodes are merged, we need to make sure they have a specific order. And this pointer, is just a number, some arbitrary random number. And so obviously we do not have a specific order. So the solution is to provide this set with a custom functor and to give it some type of ordering that will ensure that nodes are always merged from the inside out. So inner nodes are always smaller than our outer nodes, so we can essentially use that to assign priority to any given node. So let's look at this. Let's go. This will be in our Quadtree Element class here under collision info. We have a struct node comparator. And let's look again at that standard less thing here. So we see that set takes in standard less as its compare type. And it says here specifically that it does say class compare, but there will be inherent requirements of whatever type this is that it has to fulfill. And we can see here if we go to the requirements for a compare type as used in the standard library, it has to have a certain function here. And you could read through all this, but I think it's easier to just look at standard less and see what it actually is. So it has this operator parentheses that takes in two things, a left-hand side and a right-hand side. So that's all we need. That's all we need in our node comparator to make sure that it'll that a set will accept it, and any of the STL classes looking for a compare type will accept this. So we need a Boolean operator parentheses. It takes in a right-hand side and a left-hand side, and it's const. So what this is, I've said the word functor a few times. Functor is just an object that is to be evaluated as a function, because what this lets you do, just to write this in a dumb place, I could have a node comparator like, I don't know, C, and then I call it like that. I call it like it's a function. That's what overloading or overriding this operator parentheses does. It allows you to call it like this, and so it's kind of a way to pass around functions without using lambdas and all that. Just passing around objects that are then treated as functions. Okay, so we have like the skeleton there, but we actually need to give it a definition. I'll just do it up here at the top. So this is going to be a const bool node comparator operator parentheses. So this is just sort of weird syntax, but we define node comparator as a child class of Quadtree Element, so we have to access it like this. And all we're going to do here, well, first we actually do have to check if both A and B are non-null pointer, because I just learned this by writing it, that the STL classes call this regardless of how many elements there are in the tree, or the container. And so even like the first time you're inserting it, it'll give you one of these as a valid pointer and the other will be null pointer because there's nothing else in the set. So just first check that both of those exist. Otherwise, if they don't both exist, then it doesn't matter because we're only inserting one thing, so the priority of it doesn't matter. But if they do both exist, then we need to make sure that smaller inner quadrants are merged before the larger outer quadrants. And when we go through our list here, just with a for loop, just like a ranged based for loop, just like this, when you go through an ordered set like that, it traverses it in order, which like you should just know what that means. I'm not going to explain, and you probably do. But it goes through it in order, and what that means is that elements in the tree that are that have the how should I say this? Quadrants that we want to have a higher priority need to be further left in the tree. And so we can write that as follows, where a higher priority is given to A if it has a smaller dimension than B. I don't know how else to explain that, I guess. You'll just have to figure it out. But yeah, so this now we can use in our sets. We can pass this. You can see here the IntelliSense is saying type name. The default is less there, of less specialization, the key type. We now have node comparator. So we'll give that there. And then we're also going to have to take this into our set up here that actually stores our grandparents, just so that we can copy everything properly. But yeah, this will just ensure that nodes are always merged from the inside out so that there are no like stale memory issues. Now, a final note on this, I tried for a significant amount of time to come up with some way to perform, instead of just doing the safe option of performing what is essentially the maximum number of merges by merging from the inside out. I tried to come up with an algorithm to determine how to perform the minimum number by going from the outside in, more or less, but not actually having to merge the inner ones. And I just couldn't do it. I eventually gave up. And that might be like a significant performance consideration eventually if you, well, in some very rare cases where you have an extremely divided tree, like you have tons of small objects moving around, like very small. But that's like an edge case, and so I just gave up on it. But this does work. Okay, so that's move. We have update next. Update's kind of big, so I think I'll leave it at that for today. You can see up here we still have quite a few methods to do in our Quadtree element. So next time, I think we'll probably be able to finish. We'll definitely be able to finish Quadtree element. But then there's also quite a bit of work actually integrating this with our engine. So I'm not sure if we'll be able to finish that next time. But I think we'll try to. It'd be good to get through this in just two sessions. So yeah, hopefully this was interesting. Hopefully it like sort of made sense, even though I'm just going in like the somewhat nonsensical like linear order, just straight down the page here. But hopefully at this point we have enough to find where you're sort of being able to see or starting to see like the pieces coming together and understanding all of the various interactions. So yeah, I'll see you in the next lecture.